Good morning. Today we are starting a new series of lectures about change detection algorithms. So let us put these in context. You may remember these slides that we have shown in the introduction, and this is drawing a parallel between what a medical doctor is doing and what we are going to do to detect an anomaly. In our case, it is a fault. In the case of the doctor, it is a disease. So we both start by taking observation from our system, that is the patient in the case of the doctor, and then we are extracting features from raw observations. So this extracting phase can be as simple as keeping the raw values, or we can also do some filtering, some transformation to another domain, or some other dimensionality reduction technique. Once we have features, we use them to generate symptoms. So symptoms are differences between the normal features that we expect and the one that we just computed. In the case of a dynamical system, we anticipated that a way to generate symptoms is to have an observer running. That is, we have the system here, and we take observations of the output y through an observer. We compute an estimation y hat, and then we compare this. So we take the sum of these minus this. What we get is the estimation error that we call EY. So EY is our symptom. Because normally, if our observer is perfect, if there is no measurement noise, and if the system is healthy, EY should be small. So when EY is not small, we can conclude something is going on. And detecting that this is not small and something is wrong is indeed the topic of this step, symptom evaluation. The symptom evaluation step, indeed, is about defining a limit, a boundary, between what is a physiological behavior of the symptom and what is a pathological behavior. As you can imagine, this is done by defining a threshold and looking at the value of that. But actually, the thing can be a little bit more complex. So how you do this evaluation? Well, there are different ways. So we are going to go through a series of possibilities. One is implementing deterministic approaches, and the other is implementing probabilistic approaches. So today we are going to cover basic deterministic and probabilistic ones. And in the next lectures, we are showing some advanced methods that are both deterministic and probabilistic. Anyway, I want to recall that coming up to a diagnosis does involve a single symptom evaluation. But you need to do that multiple times because you need every time to validate or confute one hypothesis about the health of the system. So the first hypothesis that we want to check is the one, is the system behaving in the nominal way? So is it healthy or not? So it's simple, it is a binary hypothesis. You have just two possibilities. And this is, if you remember, what is part of the detection step. The second thing that we want to do is to run the isolation step. In the isolation step, we check a number of hypotheses, each one corresponding to one specific fault, that is, to one specific disease that the patient can have. All of these hypotheses will require us to do one symptom evaluation. Now, whenever I test an hypothesis, there are two ways I can get it wrong. So let us look at the first hypothesis, the one that is the null hypothesis, the one for detecting an anomaly. The two kinds of errors I can do in answering this hypothesis is what we call a false positive. A false positive is when I detect something, but actually the system is healthy. So I falsified my hypothesis, but I shouldn't have. And if we take the ratio of all the false positives on the total tests I do of this hypothesis, this is called the false alarm rate. So in the case of an observer, if I do a test of the hypothesis for every sample that I get, so every sample in time I do one, so you see easily that I am doing it many times, so I have a lot of tests. I just look at the number I get false positives, and I compute this rate. But I can also do a mistake the other way around, and this is called false negative. This is the system has an anomaly, but I didn't falsify the hypothesis, so I didn't detect it. And the ratio of false negatives on the total test is the missed detection rate. Indeed, I should have detected something, but I didn't. So you can imagine that a good symptom evaluation algorithm would have low false alarm rates and low misdetection rates. This is what we want, because if we have a lot of false alarm rate, people will get wary of all these alarms and will start ignoring them. So this happens all the time in the industry in real situations where the control system is signaling something, but people working in a plant know that that is not real, so they simply ignore it. And of course, the bad thing is like what happens in the child story of Pete and the wolf. So when you have a lot of false alarm, you ignore them. But when that alarm is true, you ignore it as well. And very bad things happen. On the other side, misdetection rates are some way more acceptable from the point of view of people operating the system. You know that the diagnosis system is not perfect, so you know that some alarm will be missed. So if you know that this number is pretty much 0, and this number is low, well, you probably have a good detector in practice. You may ask, why don't we get a perfect detector where both the miss detection rate and the false alarm rate are 0? Well, the reality of that is it is impossible. As we are going to see later, there are good reasons why if you try to decrease one, you increase the other, and the other way around. So it is like having a short tablecloth. So if you pull it one side, then you are uncovering the other side of the table. There is no way to have both optimal. Now that we provided some context about that, we can finally present the change detection algorithms. They are building blocks for evaluating symptoms. And they are used, as you can figure out from the name, to detect whether there is a change. A change in what? A change in the symptom. So normally we assume the symptom is pretty much 0, which is, from the point of view of the doctor, there is no symptom. So everything is behaving as nominal. But at some point, when you start having a fault or a disease, the symptom will appear. It can be an abrupt way of appearing, it can be an incipient way, or can be an intermittent, as we covered in one of the previous lectures. But we need a way to detect this onset, this change. So in general, a change detection algorithm has no knowledge that we are using it for doing fault detection. So change detection algorithms are quite general things. So what they do is they look at the signal and they check for a change. We need a way, of course, to specify what is nominal and what is not, but we will see that. So indeed, the signals that this detection is going to look at, in our case, are the signals generated by our higher level blocks, so the symptoms. So if we can combine one way to generate a symptom plus a change detection algorithm, then we get a complete diagnosis method. Before moving on, let us introduce some common notation and terms we are going to use throughout the rest of these lectures. So first of all, the signal that is going to be checked by the change detection algorithm will be denoted by Z of K. And this notation is telling us that Z is a discrete time signal and K is the discrete time instant. So what we are looking at detecting this situation. So before some time instant that we denote k0, the z behavior is nominal. And nominal is described by some parameter θ1. And after that, so k0 is the onset of our anomaly. Then the behavior is non-nominal and is described by some parameter θ1. So the situation is similar to this. So if we make a simple plot over time of z, sorry, this is k. Okay, so what we expect is that we have a nominal behavior, and to make things simple, θ0 is describing just the amplitude. So we look at the amplitude of z, and before the onset we have a θ0 value, and after that we start to have the non-nominal behavior, and this is described by a value θ1, and the moment that we have it is k0. Okay, so what the change detection algorithm needs to do is to estimate two things. We want to estimate the moment that we have this onset, and we want to estimate the new value of the parameter that we have in non-nominal condition. So maybe this is not clear to read. This is θ1. So let us start by introducing some simple deterministic methods to do this. So the first approach used to detect changes historically is called a limit check. And it is based on some simple knowledge that usually you have about a behavior, a nominal behavior of your system. So your knowledge is what is the minimum value that we expect and what is the maximum value. Everything in this range is okay. As a simple example, so let's go medical again, we can look at your heart rate during rest. So your heart rate during rest, you can test. I'm not really at rest. But it's something that should be between 60 and 100 beats per minute. So I'm not a doctor, so maybe these numbers are not the correct one, but they are reasonable. So what we expect if you are going to measure your heart rate over an extended period of time is to see this. So we set our bounds. This is the max. This is the mean. And the signal is going to stay inside, 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 up. You are dead. No, you are not dead. But anyway, here something probably something is happening there. Probably simply you are no longer at rest. So this tells us immediately what are going to be the advantages and disadvantages of using this approach. So the advantages is that this approach is simple. It is simple in two ways. It is simple to define. So it didn't take so much effort from our side to define it. It is just two numbers. And it is simple to check. Because indeed, you just take the instantaneous value of z and you compare if it is in the range or not. The disadvantage is, as you can imagine, is first, it is over-conservative. And the second, it works only in steady state. Indeed, when we define these two numbers, you see this is quite a wide range. And this is because we need to account for a lot of possible physiological variation. So there are persons that normally has a lower heart rate, persons that normally have a higher. And so all this variation is described by this range. But also, when you say to somebody at rest. So this is your heartbeat, heart rate at rest. Well, being at rest is not really well defined. So do you mean that I am sitting down and doing perfectly nothing? Or do you mean that I am standing up like here and just talking to somebody? So in these two conditions, the heart rate is different. And for people, they can still be the same situation. I mean, I'm not running. So in order to account for all these possible variations, this range needs to be big, which means that every detection algorithm using that is over-conservative. So it is really taking a lot of change to make this variable get out of these bounds. On the other side, this kind of check is working only in steady state. So as we just shown in this example, maybe your heart rate can get outside of this for some good and normal reason. If I start doing something, if I start running, or if I get scared or whatever, I can get outside of this limit, but I am not ill. There is no way in the limit check approach to encode this, because this information is a sort of model of the system. So you have a model of your heart rate, you know that when I start doing anything different, running, this is going to increase. But how is it going to increase? Well, we don't know. So limit checking is a very simple approach. So we just know that if you stay at rest long enough, let's say 5 minutes, after 5 minutes, your heart rate is at some constant steady state level. And so this is the only conditions where limit checking is really working. Of course, you can use limit checking on the entire spectrum of behavior of the system and have some very large range. For instance, I can say the heart rate is never less than 40 and never more than 200. And this is covering every possible activity and situation. If I get outside that, okay, there is an issue. But probably if I get outside that, I am also dead. So you see, it's not so much useful. So limit checking is some very basic approach to detect some very big anomaly, something that is so clear it is here, you cannot miss it. But of course, we are going to introduce later also some smarter way of doing checks. The example we have just introduced is assuming two things. So two simplifying assumptions. One is that it is enough to look at the instantaneous value of the variable z. The other is that z is a scalar. In a lot of situations, these things are not true. So it may happen that z is an output of a system with many sensors, and so it is going to be a vector, not a scalar. Or can also be that we want to check the behavior over a time window, not at every single point in time. You can imagine that doing that over a time window can have a lot of benefits from the point of view of reducing noises or other distortion in the measurements that are not by itself an indication of a fault, but they are just measuring noise. So how are we going to do that? Well, it is quite simple. We can turn this problem into the previous one, the one of checking a scalar, if we introduce what we call an evaluation function. So we take our z that can be a vector, can be a scalar over a time window, can be a vector over a time window, can be a matrix, whatever, can have any dimension in space and time. And we apply to it a function f, and this function f has an output that is scalar. So my function f is going from some big domain, let's say n by m, the reals, and this is mapping this back to R. And then we are good to go because we can simply use a limit checking, again, on a scalar variable. So an example of that could be a function, an evaluation function, that is computing the instantaneous vector norm of my variable z. This can encode, for instance, something like the orbit of a satellite. So let us assume that normally, so we have Earth in the center, and then we have the position of our satellite. Normally, it is orbiting along this trajectory. But at some point, we have issues, and the orbit changes. So let us assume bigger now. So we go to this new orbit. Okay, if we look at the problem I just drawing it in 2 dimensions, but otherwise, this is moving in 3-dimensional space. So if we look at a plot of over time of this big Z, so the result of evaluating the function f over the small z, what we expect is that we have first a low value. So this corresponds to the radius of the normal orbit. And then we start moving to the big orbit. And so you can do this to data that has different dimensions and kind of data. So it can be also data that is complex, or can be other kind of multidimensional data. So in general, if you have a vector, there are different ways to apply the evaluation function to that. So one way, as we have just shown, is to apply the norm to your vector, and then your limit check is based on the norm. This means, as we have just shown, that we look at possible values of this vector, and we defined a limit based on the norm, which turns out to be then a boundary that is a circle. So everything inside this circle has a norm that is equal or smaller than some maximum value. So as soon as you are inside, this is fine. If you're outside, it is no longer fine. So this, anyway, is the Euclidean norm. So this is what we call normally the true norm. But it is not the only one. You can also do the same kind of check on every component of your vector separately. From a graphical point of view, this can be represented like that, like this. So we introduce a boundary that is a rectangle. So why we get a rectangle? Because if we do the check on every component separately, then we need to define what is the minimum and maximum value along the first dimension. So we have this Z1 min, and what is the maximum? So Z1 max. So this is the component Z1. This is the component Z2. So similarly, you have a mean and max over Z2 as well. And if you take all the points that are with the Z1 component between mean and max, and the Z2 component between this other mean and max, well, you get a rectangle. Everything inside the rectangle is matching that condition. But this is not the only way. So in general, you can apply a P norm. So you get different shapes. And on the extreme of these, you have the zero norm, which basically tells you whether you have one component in the vector that is non-zero or not. Or you can have the infinite norm that is telling you what is the largest value in the vector. Or you can have some more general approaches. So let us assume that the shape of these clouds of points representing valid, healthy values of the variable z is something complex that cannot be approximated good enough with either a circle, a square, or some other shape in between. Then we can introduce a set-based approach. In a set-based approach, you define the boundary the way you like. So it can be that normally you have these complex distributions of values for z. Then the best thing is to define a boundary like this, with a shape that is completely arbitrary. So this approach is called set-based. And this is what a lot of classification detection algorithms in machine learning are doing. So if you know something about support vector machines, SVM in short, they are doing actually this. So I'm not going into the details of that, but they allow you to define a boundary that is some way arbitrary. So if you see, even if the limit checking algorithm in its basic vanilla formulation is quite simple and not very performant, if we can extend that with an evaluation function, well, that's not so bad anymore. So we can pre-process data Z such that we can do a lot of checks with arbitrary shapes. And this is just over space. But we can also have different ways of checking the variable z if we consider it over time, because we are taking measurements from a dynamic system, so we have measurements at every sampling time. So indeed, if we look at the behavior of the signal z over time, again, we have different ways of evaluating that, and again, it involves using different norms. So let's go back now to the case of a scalar z, which is easier for me, of course, to draw, because now I need this extra dimension for the time index. So this is the time index, k. If I have a signal that is normally 0, 0, 0, then some value, 0, then some other value, then 0 again, 0 again. Well, one thing that I can do, the simplest, is I take a time window, so a number of samples on a time window that is actually rolling. So let's say at every time, I consider the last 5 seconds of my signal, and I check. What I'm going to check? Well, the first example, the first thing that we can do is to use what is called the L0 norm. So again, we have a way of defining a norm based on a number. So we had 0 norm previously when we looked over space. When we look over time, we have the L0 norm. And the L0 norm is telling us the number of samples that are non-zero. So we have in this example 1, 2, 3. The L0 norm of this is equal to 3. But I can also do another thing. I can look at the peak value of the signal over a time window. And this is equivalent to computing the L infinite norm of my signal. So again, same example. If I apply the L infinite norm, what I get as a result is the value of this. So the value of the max, the peak value in the time window is the L infinite norm. But you have a lot of other ways of evaluating that. So you can apply one LP norm, like the L1 norm, that is also called the Manhattan norm, or the old root mean square of the signal, which is the L2 norm. So let us indicate that on the same plot. So if you compute the L2 norm of that, you are getting something like probably something like this. This is probably the L2 norm of this signal. Anyway, there are the same advantages and disadvantages as before. Because the idea is the same. I take something that has more than one dimension. So over a time window, I have so many samples, and convert that to something that is a scalar. So the value of the norm over that time window is a scalar, is again a signal. So to make this anyway clear what I mean. So when I say time window, a rolling time window over time, I mean that we have possibly a lot of samples, but at a given instant, I am looking at all the values that I have in this window, in this time window. So this is my window. So at this instant k, I'm looking at the samples I have at time k, k minus 1, k minus 2, minus 3, up to some k minus n that is here, where n is the length of the window. When I get to instant k plus 1, I'm taking this window and moving it one step forward. So now I am looking at here. So I get a new sample in my window, the one at time k plus 1, and I'm dumping one old sample that was here, so the k minus n sample. So the first sample that now I'm looking at is k minus n plus 1. And I repeat it all the time. So every time I get a new sample, I move my window forward. So one little downside of this is that you need a buffering, let's say. So before time k bigger or equal than n, so before time n, I cannot fill the entire window. So either initially I start with windows that are shorter, or I need to wait some buffering to fill my window. Okay, still there is one case that you may wonder about. So what happens if I have a signal that is both multidimensional, a vector, a matrix, or whatever, and I want to evaluate it over a time window? Well, the answer is simple. You combine the two approaches. So first, you take the norm in space, and then you take the norm in time. So let us make the example of the satellite again. So if you have your satellite that is orbiting, you have several samples. Now I'm making an example in 2 dimensions. So these examples have 2 components. So the first step would be to take the norm. So you take this sample, for instance. You compute the length of this vector. This is the norm of the position of the satellite. And if you do it for the orbit at different times, what you get is again a signal. So we have the time index k here. Here we had z1 and z2. So now we are getting, so let's use different colors. So we use the green for this norm. So now we have values of this. And then you have your signal over time, and you can define a time window here, compute the L something norm of it. So in the end, you get to the same result. You get a single scalar number at every time step, and that is the one that you are evaluating in the limit check. So we see that even in this formulation, limit checking in the end is quite flexible, but there are ways to improve it. We can combine it further with approaches that allows to have this limit to change over time. And that would be definitely a great improvement. For the example of the heart rate, I would like to have a limit that is good for resting, and a limit that is good for running, a limit that is good for swimming, and so on. And if I have a way to tell what the patient is doing, then I can have this limit changed over time dynamically. So that would be the first improvement. So the way to change these limits can be either based on some other information that we have, which some ways imply that I have a model on how these limits should change, or they can be relative on the signal amplitude itself. So this is a way to detect some way steady state. So I could have a situation like that. I have a signal that is going through different steady states. I have this steady state and this other steady state. So this could be your heart rate at rest, your heart rate when you do something else, or it can be the RPM of an engine. I don't know initially what these values are, but I just know that I'm going through steady states. So what I can do is I take a time window here and I define bounds around it. So I can have bounds that are, for instance, plus or minus 10% of the steady state value. And then I have new bounds here that are plus or minus 10% of this new steady state. So you can do that. Of course, there is a disadvantage. So you can't say anything during the transient. You have no way. And you also need to wait for the steady state to be reached. So when you are here, you don't know yet that you are at steady state. You need to wait for some number of samples, let's say until here, to say, okay, my signal was constant enough in the last time window, so let's say I am at steady state now. This approach is particularly good if all that you want to detect is some anomalous spike or other behavior, like this. So if you have a spike like this, then this approach, or something like this, then you are going to detect it very easily with this approach. But what if we want to go even further? Well, there are two ways of going even further. So the one is actually to have these bounds change over time according to the conditions of the system. And to do that, you need an accurate model of the system. So model-based approaches are going to do that. But there is also another limitation in the limit check approach that we didn't stress enough. So the limitation is, let us assume you have this, a single sample that is out of the bounds. How do you classify that? Do you classify it as a fault that is lasting for a single time instant? Well, that's some way unlikely. Or maybe you just think, well, probably it was measurement noise. There was something going on with the sensor. I bet you are saying the second, because that's very common, and we usually go for common explanations. Well, this kind of reasoning is actually what is done in probabilistic checks, which are actually encoding this very fact about measurements that are affected by randomness. Randomness is the noise that we have. Or randomness can also be some other external condition, like if it is the position of something, maybe something went there and touched it lightly. And your position sensor detected this small movement. But it was not a fault by itself. Okay, it was some external influence that is gone, so will no longer happen. So these kind of disturbances are more likely than a fault. Indeed, measurement noise is there, always. Other environmental disturbances like wind, people touching your system when they shouldn't, they will always happen. A fault in a normal system that is run properly is a rare condition. So you want a way not to be always alarmed by these very short and very common events, and instead to be alarmed when we have something that is big and lasting enough, like this and this. So these two things are quite an unlikely behavior for a healthy system. And probabilistic limit checking approaches allows us to have a mathematically sound formulation to tell apart this red faulty behavior from this blue random, noisy, and healthy behavior.